Welcome. This is a video presentation of the paper, A Universe from Itself, the Geometric Mean Expansion of Space and the Creation of Quanta, Part 6, the Creation of Quanta. The geometric mean expansion of space produces a geometric mean counterpart to the energy of the universe. Using our geometric mean relationship, we know that the energy of the observable universe times its small energy counterpart is equal to the initial energy squared. Solving for our small energy, we find C times h bar divided by r sub h, where r sub h is the radius of the hyperverse. The geometric mean expansion of space produces a geometric mean counterpart to the radius of the universe as well. And again, the radius of the hyperverse times the geometric mean counterpart, small radius, is equal to the initial radius squared. Solving for this geometric mean counterpart, we find the small radius is equal to 4 times the Planck length squared divided by r sub h. These geometric mean values are related. We find that the small energy is equal to the small radius times the speed of light to the 4th power divided by 4 times the gravitational constant. And these geometric mean values are related in a manner similar to the energy and radius of the observable universe. Our equation for the energy of the observable universe, E sub O, is equal to the radius of the hyperverse times the speed of light to the 4th power divided by 4g. We see a very similar structure between these two equations. If we take our equations for small energy, divide each side by r sub s, the small radius, we find that the small energy divided by the small radius is equal to c to the 4th divided by 4g. Similarly, with the energy of the observable universe, we'll take the ratio of the energy of the observable universe divided by the hyperverse radius, and we get the same value, c to the 4th divided by 4g. This particular relationship will become very important later in the series. Let's now look at angular momentum. L, our term for angular momentum, is defined as mass times radius times the tangential velocity. The angular momentum of the observable universe would thus be the mass of the observable universe times its radius, r sub h, times the tangential velocity. We've defined that to be the square root of 2 times c, and we keep that constant. The product is the square root of 2 times h bar times this term, which pops up all the time now, r sub h divided by 2lp quantity squared. Previously, we did not bother to calculate the geometric mean counterpart of the large angular momentum. We are now going to insert our small mass, our small radius, and our constant v sub t. The product is the square root of 2 times h bar times this term here. You notice that these two are the same, except this is 1 over r sub h divided by 2lp squared. The initial angular momentum we determined to be the square root of 2 times h bar. So if we take this term and multiply it by this term, these would cancel, and we take the square root to get the geometric mean, we get the initial value. This is a very interesting observation that we get from using the small mass and the small radius. So the small radius and the small energy, or mass, are deeply related, but there's a problem. The energy and radius represent two different entities. That is, the small radius is not the radius of the small energy. In our hyperverse model, the blue squiggly line here represents the three-dimensional surface volume of the hyperverse. And this is the radius, this is the center. We exist along the surface here. And remember, this is a 4-dimensional structure put on 2 dimensions, so we have to deal with that. The surface, again, is our 3D universe. The radius that we measure is the radius of the hyperverse. And we know the energy of it. So there's no question the radius and the energy are connected. This is the radius for this particular energy. But in the case of our geometric mean counterparts, this is not true. So let's now take a look at what brings us to the conclusion that they are different entities. Let's first look at the small energy value. The energy of the observable universe is R sub h times c to the fourth over 4g, and our small energy, or geometric mean counterpart here, is c times h bar divided by the radius of the hyperverse. So let us ask how many small energy units exist within the observable universe. To do this, we will divide the energy of the observable universe by the small energy value. We have the terms here, and we find the answer to be r sub h, the radius of the hyperverse, divided by 2 Planck lengths squared, and that happens to equal to about 10 to the 122 power. So there's that many small energy units within the energy of the observable universe. Next, let us ask what the volume is of a unit of small energy. Okay, to calculate the volume, V sub SEQ, which could just as well be V sub S for small, but this is small energy quantum. This is where we're going with this. We'll take the volume of the observable universe, and this is the equation for the surface volume of a four-dimensional sphere, 2 pi squared r cubed. Of course, we have radius of the hyperverse. We know there's r sub h divided by 2lp quantity squared units of small energy quanta. So we want to know the volume divided by that many units, and we find the volume of our small energy quantum is 2 pi squared times the radius cubed. So taking our equation for the volume, let's ask what is the radius of that volume. So to get the radius, we'll take our volume, which we know to be 2 pi squared times this particular value, divide each side by 2 pi squared, cancel out, take the cube root, and we find the radius of our small energy quantum is equal to the cube root of the radius of the hyperverse times 4 times the Planck length squared. And numerically it works out that the radius of the small energy quantum is approximately 6.5 times 10 to the minus 15th meters. And notice this does not match the small radius value. Our small radius, r sub s, 4 times the Planck length squared divided by r sub h, is approximately 4 times 10 to the minus 96 meters. So we have quite a difference here. Okay, we're going to switch over to the small radius now. So let us look at the geometric mean counterpart of the radius of the hyperverse. We've seen r sub s quite a bit now. This is a small radius, and it's determined by dividing the initial radius squared by the hyperverse radius, and our answer is 4 times the Planck length squared divided by the radius of the hyperverse. R sub s is going to be mostly shown as r sub srq. This stands for small radius quantum as compared to small energy quantum. So let us now look at what the energy is that's connected to the small radius. And we'll do this by taking the volume of the observable universe and dividing it by our volume of the small radius quantum. So we'll divide our 2 pi squared r cubed, radius of the hyperverse here, by 2 pi squared r cubed for the radius of the small radius quantum, and these cancel out and do the math, and we get at the end r sub h divided by 2 Planck lengths to the 6th power. Now, to get the energy connected to the smaller radius, we'll take the energy of the observable universe and divide it by the number of small radius quantum units. The number of small radius quantum units we've just determined here. So we take our E sub O value and divide it by this number, and it's identical to this. These are just two different ways of expressing it. Taking our energy value from the previous slide, we know that the energy of the small radius quantum is equal to the energy of the observable universe times our factor here, and it comes to about 2.77 times 10 to the minus 296 joules. So we are seeing they are distinct. Our small energy quantum has its own radius. And our small radius, the geometric mean counterpart of the radius of the hyperverse, has its own associated energy, its small radius quantum energy. So although the small energy and small radius are related and look like they really belong together, they have separate identities. So we have identified two scales or levels of quanta, the small energy quantum and the small radius quantum. Notice again that the equation of the small energy quantum is c times h bar divided by r sub h. And as pointed out previously, this is the same form as the Planck relation. And notice that the radius of the small energy quantum is about 6.5 times 10 to the minus 15th meters. The Compton radius, or reduced Compton wavelength, lambda bar, for in this case the electron, is equal to h bar divided by m, the mass of the particle, times the speed of light. And it comes to about 3.86 times 10 to the minus 13th meters. The Compton radius of a proton comes out to about 2.1 times 10 to the minus 16th meters. If we take, for example, the geometric mean of the Compton radius of the electron and the Compton radius of a proton, we get about 9 times 10 to the minus 15th meters. Now we already calculated the radius of our small energy quantum to be about 6.5 times 10 to the minus 15th meters. It appears that the small energy quantum is the quantum of our quantum mechanics, and that the small radius quantum is the smallest quantum. The small energy quantum is composed of RH divided by 2LP to the fourth power units of small radius quanta. The small energy quantum is derived as the geometric mean of the hyperverse energy. That energy value is given by c times h bar divided by the radius of the hyperverse. Alternatively, we can express it as so. The mass is h bar divided by c times r sub h, and can be expressed as so. And the radius is the cube root of the radius of the hyperverse times 4LP squared, and can also be expressed in terms of RH over 2LP. Numerically, the small energy quantum energy is about 1.2 times 10 to the minus 52 joules. The mass is about 1.34 times 10 to the minus 69 kilograms, and the radius of the small energy quantum is about 6.5 times 10 to the minus 15th meters. The small radius quantum is derived as the geometric mean of the hyperverse radius. Its associated energy value is c times h bar divided by r sub h times this factor here to the fourth power. We've got its mass, we have its radius. Numerically, we know the radius is the small radius at about 4 times 10 to the minus 96 meters, but it has a particularly small energy of about 2.77 times 10 to the minus 296 joules. So we see that the geometric mean expansion of space is producing two quantum levels. The small energy quantum is the quantum of our quantum mechanics. It has its own energy and associated radius. The geometric mean expansion of space produces a small radius, and it has its own associated energy. The geometric mean expansion of space creates a small energy value and a small radius value. They are deeply connected, conserving the ratio of energy to radius and conserving angular momentum. Despite this, the energy and radius are not the energy or radius of the other. They have separate identities, and this difference will prove to be very important.